Now let's talk about hash tables. So hash tables are one of the core data structures that we have, but they're also one of the most important, and their primary use is for finding things very quickly. So imagine you gave me an array and you told me within this array there were strings, but I don't necessarily know what's there. So it could contain cat, and it could contain horse, and it could contain dog, and it could contain mouse, for example. If you were to ask me, does it contain rabbit? If I knew nothing about this array other than the fact that it might contain this string, well, the way I might try to determine if rabbit is there is to perform what's called a linear search. And that is, I'd start on one end and I'd look here and say, is that rabbit? If the answer is no, then I move over here and say, is that rabbit? No. Is that rabbit? No. If it turns out rabbit is here, then I'll stop. But if it's not there, the only way I can really know that in this case is to look at everything. So how many comparisons do I have to make, potentially? Well, in worst case, if there's n positions in the array, then I have to make n comparisons. That is, I ask n different times, is this what I'm looking for? So that's one of your worst case scenarios in terms of what you could potentially have to do to find something in some type of data structure. Because imagine n is very big. If there's a million things there, do I want to have to ask that question a million times? If there's a billion, do I want to have to ask it a billion times? The answer is no. So can we do better? Well, if you told me this array was sorted, and so it might have things like this. So A would be here, B would be here. Maybe we jump to E because there is no D or C. Maybe there's G. We'll have some more. Maybe Y is down here. G. We get something like that. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 things here. So if you ask me, is S there? If it's sorted, I can perform what's called a binary search. And if you've seen my video on binary search trees, the underlying property is the same. What I would do here, if I know it's sorted, is I'm going to figure out where the middle is at. So the middle is going to be this, I think. 1, 2, 3, 4. 1, 2, 3, 4. So I'm going to look there and say, is this what I'm looking for? No, that's not S. But because it's sorted, I know that if S is there, it has to be on this side. So now I'm going to calculate a new middle. And depending on how you choose to split, since there's an even number of things here, I might say choose this. And say, is that S? Well, if not, I'm going to do the same type of thing. So I know that if I've just split and found the middle, then it has to be to this side. So now it has to be here if it exists. So I'd ask, is there S? Depending on how I split, maybe I end up checking there. That's not S. So now I know it has to be down to this point. Is that S? No. So I know that S isn't there. But because it was sorted and I'm performing a binary search, at each comparison, I'm basically eliminating half of what's currently available. I eliminated this half. Then I eliminated this half. Then I eliminated, say this half or whatever. So how many comparisons is that? Well, if we think about the tree, again, for a binary search tree, let's say I have this. Or if it's a binary search tree, we know everything on the left side of a particular node has a value less than or equal to the parent node, and everything to the right is greater than. Well, in this case, I have, 7 things, or 7 nodes. And so what's the worst case scenario? Well, if it's not here, I go down a side, maybe I go here. Well, if it's not there, I go down a side, maybe I go here. Well, I had to ask 3 questions. So what I had here was log base 2 of 7, which is about log base 2 of 8, which I can do the math on. That's 3. So 1, 2, 3 questions. So log 2 of n is much better than n. So this is a better choice than this. But can we do better? Well, it turns out the answer to that is yes. So what if we have my array again, and we have indices, right? 0, 1, 2, 3, dot, 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 down to n minus 1 if there's n positions. And what if I told you there was a function, and when you gave me the thing you're looking for, say rabbit, what I spit out in some form was the index into the array. Well, then if you put in rabbit and it says look here, I can look there and either rabbit is there or it's not there. But the benefit of this is this doesn't take long to calculate. So whether my array has n equals 10 positions or n equals 1 billion positions, the cost to calculate the index is the same. So this is extraordinarily fast, and that's one reason why hash tables are so popular in certain cases. All right? So if hash tables are so great, why haven't we been using them? Well, let's look at a couple issues. But let's talk about now what this is. So instead of f, really what we have is a hash function, and we store key value pairs in most cases. So the keys are unique, and you would plug in a key and it gives you some number, and ultimately we use that number to get an array index. So let's see one issue and why I'm writing it this way instead of just saying we get the array index. So in the Python programming language, and you don't have to know Python to do this, it doesn't matter, but the Python programming language has hash functions built into it. So let's see what kind of values it gives me. Hash cat. There's a negative sign, but this is a monstrously huge number. A lot bigger than the number of array indices you can have because you can't have enough memory to represent that, right? Let's try something else. Let's say Kate. Doesn't have to be a real word. Well, now I got a really big number that's nowhere close to this. Well, let's try cat D. Well, that looks similar, and it is actually right next to this one. That's pretty close to this. Let's try car. That's closer to this. But the point here is we're getting these monstrously huge numbers. All right, so how does that help us? Well, this is what I meant by we get this number, but as we can solve there, that at least for that hash function, it generates numbers much bigger than I can have array indices. And in fact, it's probably not even tied to the size of the array. So what do I do about it? Well, what I do is I take my number, hash my key, we take this, whatever the value is, we apply mod n to it, where n is the number of array elements, which forces, now this right here will generate integers, and if we deal with the negatives, we can deal with that as well. But this would generate integers in the range of 0, 1, 2, dot, 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 n minus 1. Because imagine we had this, let's say n was 4. Well, then if we get, and I'm only going to deal with non-negative numbers potentially, so I don't have to look at everything. But remember how the modulus operator works. It's the remainder from the division. So if I have 0 mod 4, this is 0 divided by 4. 4 goes in there 0 times. 0 times 4 is 0. So we get 0, so the remainder is 0. So this would be 0. 1 mod 4. That's 1 divided by 4. 4 goes in there 0 times. 0 times 4 is 0. We get 1, so remainder 1. So this is 1, and so forth. What happens when we get 4? 4 divided by 4 goes in there 1 times. 1 times 4 is 4. We have 0 as the remainder. So we roll back around to 0, just like 0 mod 4 gave me 0. You can never get the number that you're using here as a remainder, because that means you could have divided one more time into something. And so then 5 mod 4 would be 5 divided by 4. 1 times 4 is 4. This has 1. The remainder is 1. So we basically have wrapped around. So even for really big numbers, we get numbers that look like this. We wrap around because of the modulus operator, so everything will always be within this range. Okay, so we've dealt with that issue. That's not really a problem, but it does force our numbers, which could be in a huge range, down to the range of 0 to n minus 1. So that's fine. That doesn't take much time to apply the modulus operator. So what's the actual issue? Well, let's say we do this. I have my array. And let me draw it like this to make it easier for me to write stuff. Well, let's say there's 4 positions. So my indices are 0, 1, 2, and 3. And we say we get hash of cat. And then we apply mod 4 to it. And so whatever number I get, then after mod 4, let's say gives me 2. So it means I'm going to put cat here. But then let's say we put in hash snake mod 4. And I also get 2. So snake goes here. But I already had cat there. So they can't both be there. Now how could this have occurred? Well, it could be that the part before the modulus 4 is the same, or it could just be that after the mod 4, it basically wraps around. So as we saw, if hash of cat was 0, then mod 4 is still 0. But if hash of snake was 4, 4 mod 4 is also 0. And then if we had 8, 4 divides evenly into 8, so that would give me 0, and 12 would give me 0, and so forth. So everything that's a multiple of 4 would hash to this position because of the modulus. And then everything that's a multiple of 4 plus 1 would be here. Multiple of 4 plus 2 would be here. Multiple of 4 plus 3 would be here, and so forth. That's how they end up at the same spots. So what do we do about that? Well, what we have here is what we call a collision. So one way of dealing with it is this. Let's say that cat goes here, and we already had dog here. And so then when we get hash of snake, and we know that it's supposed to be here, a way of dealing with it says, well, this spot's already used, so let's go looking for a free spot. So I'll start here and I work my way down. So I look here and say, well, dog is already there, so let's look for a free spot. We come around and we find a free spot, so we actually put snake in this position. Now we can do that up to a point, but eventually this thing is going to be full, which means for this approach, if there's n positions, we can only store n things. That's one problem with this approach. So we'll call this problem 1. But what's a bigger problem? And this will be true for all hash tables. The more collisions we have, the more work we have to do to resolve the collision, which slows things down. I thought we said that the reason why people use hash tables because they were so fast. But they're at their fastest when the place that something hashes to is empty and we just store it there. So collisions cause problems. Let's say that. And slow things down. Negating the benefits of hash tables. This is true no matter what hash table you use. There's always a potential for collisions. That's just the way it is. And in fact, there's something called the pigeonhole principle. And it says that if you have M positions and N things to store, right? N things to store, and N is greater than M, then you're guaranteed that two things have to go to the same spot. What does that look like? So here I have M equals 3, and let's say N is equal to 4. Well, maybe I store something here, then I store the second thing here, then the third thing goes here. So far I haven't had a collision, but what about the fourth thing? It's guaranteed to hit one of these spots. So what do you do about that? We'll make this bigger. If I have more slots, then maybe the fourth thing goes here. That doesn't mean I couldn't have had a collision, that I can't still have multiple things hashed to the same spot, but it at least has the opportunity that everything went to a different spot. Whereas if the number of spots is less than the number of things you need to store, you're guaranteed of a collision. So how can we deal with that problem? Well, there's a way of dealing with that. Let's say we start with 3 slots, which really nobody would really do because you know you're virtually guaranteed to have problems. But let's say we do this. So we have a collision. And whether there's collisions or not, let's say we had to store 3 things. And maybe they all went to different spots, so there was no collisions. Or let's say that 2 of them really went here. So this was X1 and this was really X2. That's where we put the second thing that hashed to this spot. One of the things we can do is grow the space, right? Which means now for a fourth thing, even if it hashes to one of these positions, we can now put it in a spot on its own. So we don't have to have sharing in any way. In fact, this doesn't allow sharing. Things are just stored in their own slot. But what's the problem with that? Well, I do have to grow the space somehow, but if you've seen my videos on dynamic memory allocation, we could use the reallocate function to grow this array, because maybe it's an array of structures, for example. There's other choices. So I could regrow the space, but there's another issue. We need to rehash everything. Because imagine before I had this. Let's say that these are my indices, 0, 1, and 2. And let's say that when I hash cat, I would have mod 3, because there's 3 things here. And let's say that what I get is 0. But the way I got that was I had that hash cat itself was equal to 3. So 3 mod 3 is equal to 0, which means instead of putting something here, it wrapped back around and it goes here. Well, if I grow my space, then that means cat wouldn't really go here because there is a index 3, right? Because now I have, say, hash of cat mod 6, and if I had 3, then it would go to this position. So everything here, when I regrow the space, needs to be rehashed to see if it belonged there in the first place. Maybe it really did just go to 0 because that's what you had before using the modulus operator, or if it got there by wrapping around then it needs to potentially go to a new spot. It could be that even after the growth, it still wraps around and goes somewhere, and maybe under some circumstances it's still that same spot, but there's going to be lots of things that wouldn't have went to that same spot, so everything needs to be rehashed. Well, if I'm doing all that, that takes time, and once again, that slowed down the hash table, which means things aren't faster. So what do I do about that? Well, there's lots of ways to resolve these problems, but there's still always the potential for collisions. That can never go away. But for this particular problem, what I'm going to do is this. I'm going to have my array be a fixed size. So there's n slots here. And you say, well, but what if I want to store more than n things? How do I deal with it? Instead of storing the things here in these slots, I'm going to make each of these slots be the head of a linked list. And so this solution is called chaining. So I'm resolving the collisions with chaining. So what happens now, let's say I have this, you want to store cat. And let's say that hash of cat mod n for the number of slots here is equal to 2. So 0, 1, 2, 3. We'll do that. So that means cat goes here. So I'm going to add a node to my linked list because initially these are all null, and put cat here. And then we get hash dog mod n is equal to 0. Dog. And these will be null terminated. And then we get hash snake mod n is equal to 2. So what happens? Now I come here and I just work my way down the linked list. If it's the very first thing like cat was, then I just create that initial node and store its address here. But instead I'm going to come down here. Now I could either put it at the head end, but for drawing purposes I'm going to put it at the end. And put it there. Now if this is really long, moving down the list to find the end takes a lot more time. It's actually just easier to put it at the head end. And so basically insert a node here. So this is what I've actually implemented and I'm about to show you. But this still has potential problems. If I really only had 4 slots and I have to store 1,000 things, well now I have a bunch of linked lists, which means that when I'm looking for something to see if it's already there, well then I'm still searching a linked list, which is basically a linear search. So that doesn't operate very quickly. So that has no benefit. So I still want this generally to be very big. And I think the rule of thumb is make this much bigger than you think you'll need, like maybe twice the number of things. If you think I'm going to store 1,000 things, well maybe I have 2,000 slots. And then you're probably going to have some collisions anyway. But hopefully there's enough dispersion that these chains aren't very long. And before we look at my implementation, one other thing I need to point out is that we're storing key value pairs. And keys need to be unique. But what if I give you the same key twice? Well, since they have to be unique, I can't store 2 of the same things. That means all I do is change the value. So if the first time I want to store, say cat is my key and Felix is my value, I can do that. But then if I give you cat again and give you Bugs Bunny, well now this is gone. I just put it in the same spot. So now I have cat bunny wherever it was at. So that's how that works. So let's look at my implementation. So here's my pseudocode. So I've actually implemented a lot of things to let me actually run it from the command line. So a lot of the code is based on that. And so here's my pseudocode, and when you look at my implementation, you'll see it matches up with this. And then here I've drawn a picture to show how I resolve collisions, which is through chaining. So here's my array of heads of linked list. And this would be a node that's null terminated, and here would be a node followed by another node, and it's null terminated, and so forth. I've used a couple other things down here that I've never talked about in my videos before. One is I'm using a pound define. Now what this is, just like a pound include is a preprocessor directive, I'm saying preprocessor, the preprocessor looks at the file before the compiler ever looks at it. So basically what it does here is it does a search and replace. So every place that I've written the word size, and I don't have to capitalize it, but that's a way of letting somebody look at the code know that, oh, this isn't really a variable, it has special meaning. The preprocessor will find every occurrence of the word size and replace it with the number 5. So pound defines can actually be used to insert code and some other things, but in this case, I'm just replacing the word size with number. And the reason for doing this is I use size at quite a few places. So instead of me either using a variable and having to pass in those variables, since I don't expect this to change as the program is running, so therefore it's not actually a variable, and this isn't a variable. If I want to change it to say 50 every place, then I just do this. That's the easy way of dealing with it. All right? Another thing I've never talked about in any of my videos is a type def. A type def essentially lets me replace some code with an alias for that. So I'm creating a shortcut essentially. So every place where I would have written struct node, now I'm using the word node like this. And once again, it's capitalized to make it clear that it's not really a variable. So you can see here, instead of writing struct node star table, I just put capital node. And so the computer will insert this for me. But this is not the same thing as this. It's not a preprocessor directive. But I'm using it in a whole bunch of places. All right? So we can compile my code. And so let's see what happens. Up here is just my code for getting something the user types in and then calling the appropriate function. Notice here, I'm creating an array of heads of linked lists. So every one of these is of type struct node star. So it's a pointer to a node. So if you've seen my linked list video, if I just want to create a linked list, I would have said something like this: struct node star head, and then typically given an initial value of null. That needs to be capitalized, sorry. See, this is the address of a struct node. Well, that's what this is, address of a struct node. I just have an array of those. So I have a whole bunch of these, and I want to initialize them all to null. So if I run my program, I run it, here's my operations that I can perform. I can add a node, delete a node, print the hash table, or stop. So let's print, and you see there's nothing there, or it's just nulls. If I try delete, say I want to delete cat, well, it says, oh, that's an error. There is no cat here. So whether I was storing some things and I hadn't put cat in there yet, or I haven't stored anything yet, so obviously cat can't be there, that's still a problem. So we'll look at these things as I use it. So let's say now I want to do an add. Let's add cat, and we'll use Felix as the value. And I've told it to also tell me what the hashed value was, and then what the index into my array is. How big was my array? I made it small to try to force collisions. So I made it 5, but to try to avoid collisions as much as possible, then this should be a prime number. And you'll get into the theory of that if you take a data structures and algorithms course. So now let's look at my linked list, or excuse me, my hash table. It hashed, the hash value itself is 312. After I apply mod 5 to that, I get 2. So this is where Felix goes. So cat Felix are both stored here. I need to store the key so I can know what key that corresponds to, because there may be multiple things that are here and I need to know which one is which. But multiple things can have the same value. The keys themselves have to be unique. So how to add values? So where's my function? So if I do an add, here's an add. And so I'm going to do Here's my function call, add key value. So I give it the array of heads, the key I want to store in the value. And so here's where I hash the value. Here's the index that corresponds to after I applied mod size. And I did these as separate steps so I could print both. Before, I actually just did this as one step. And now I'm going to use this as to make my code easier to read. I'm going to say head is equal to whatever that address is, table index. And I just go looking, starting at the beginning of the linked list that either could be there, or if there is no linked list, then I just want to add something there. So if something's already there, so let's say I do this, add cat, and now I say Tom. Now I just replace Felix with Tom because cat is my unique identifier. So first I'm going to go looking through the linked list if it exists, and if I find something, then I do a string copy to replace the value and then just return. But if I make it through the entire linked list at that array index and can't find something, then it's either there are no nodes or there are nodes, but that particular key doesn't exist. So now I'm going to come down here and add a node. So allocate memory, store the key value pair in that node, and for performance reasons, I simply just add it at the head position. So I'm going to set temp next, to have the address of the next node in the linked list. And now say table index contains the address of this node. That's how I insert. So let's go back to the top. So here's where I add. Well, if I want to delete, so let's add a couple more things to see what we get. Add snake. We'll throw in a Harry Potter reference there. There's snake. Let's add something else. I'm trying to force a collision. No collision so far. Still no collisions. And there's a collision. Horse and snake both ultimately end up at position 0, so they're part of the same chain in a linked list. All right. So what now if I want to remove, say, snake? So I can do delete, and the key is snake. And now when I look at it, snake is gone. So where was that at? So here's delete. So the function is delete key value. So let's look for that. That's down here. And so here we have to be careful because we have some possibilities. So let's look at a picture. So here's my array of heads of linked lists. Let's say we have something like this. So let's say I want to insert this node, or delete this node. Well, what do I ultimately need to do? I need to save this address, right? Because it's only stored here. Then, and this would probably be saved in temp, then I can delete this node or free up the memory in programming terms. And once I've done that, then I take the next that's here and give it the value that I saved here, which ties these two together. Right? But what if I'm here? Well, there is no previous over here to update, so the first node is actually special because I simply want to free this and then actually set this back to null. And if it's the last node, so if my chain looks like this, if I want to get rid of this, then I need to save its next address, which is already null. So I'll have temp will be equal to null. I don't write this. I say temp is equal to this position next, which will be null. Then I free this up, and now I say this next is equal to whatever temp is, which will give this null. So the end works its way out. It's the first one that's a special case. So I need to deal with that. So I do that. I start off by saying if there are no nodes at all, then there's nothing for you to get rid of, so that's an error. Then I'm going to start looking. If what you want to get rid is the first node, whether there's other things past it or not, doesn't matter. But if it's the first node, I can't really update what's to the left of it because there is nothing to the left, so I treat it as special. So I deal with it here, and then I return. And if I made it past both of these, then I'm going to go looking down the linked list. If I move through the entire linked list and can't find that key, and remember I'm trying to delete here, not add, well then that's an error because there was nothing to delete. But if I do find that key, then I want to do what I said, which is to save the next address, free the current node that you're trying to get rid of, and then update the previous address to have what was the following address. I tie those together here. So that's how I delete the key in the middle, or the key value pair. So that's this scenario. I want to delete this. There's a node to the left, there's a node to the right. I save the following address, free this up, and tie these together. That's what that code does. Right? And then let's see how I print. So print table is what I'm looking for. So how does this work? So remember what we said do here. If things are empty, I want to write null. Otherwise, I want to print everything that's on that list, like here. This had two nodes that both ultimately ended up at position 0, so I'm going to work my way down the linked list printing the key value pairs. So here's what I do. I just go through the array, and if the current value in the array is null, that means there are no nodes in that linked list, so I print that. Otherwise, I print the word key value pairs, and then I want to store the address of the first node or the head of that linked list, and then just work my way down the linked list, updating the addresses in temp each time, but printing the key value pairs. That's what I do. And then ultimately over here I can stop. So what about my hash function? Well, this is something, I don't think I made this up. This is what you might see in a textbook. It's a very simplistic way of producing a key, and all it does is go through the string, since that's what I'm using for keys, and it adds the ASCII values. That's how I got numbers that were so big, like 312, whatever. But it's not very good, I'm sure. So basically what I'm saying do here is if I had ABC, well, I know that A has an ASCII value of 97, which means B is 98, which means C is 99. All it does is add these, which is really 3 times 98. And that would be the result of hash, ABC. And then you apply mod n to it. That's what I'm doing. I'm not really up to speed on the theory of hash tables, but you would like to have something that has good dispersion to try to minimize the collisions. If you want to see something real hardcore, go to this link here at bertlebertle.net, and this guy really gets into some heavy details on it. I'm sure people get PhDs come up with a new way to create hash tables, but that's not really my field, so I can't say that I'm well versed in the process. But this is simplistic, and actually I want something for test purposes that doesn't work that well because I'm trying to get there to be collisions. But you can see I even had trouble forcing collisions here, even with a small array. But anyway, that's how hash tables work, at least on the basic level. But some people do specialize in hash tables, and the theory can get quite extensive actually. I'm sure there's books devoted just to hash tables, but I'm not well versed on what they are. But that should get you going, at least for a basic data structures and algorithms course. If you find videos like this helpful, and you haven't already subscribed to my channel, please do so because that'll help me out as well.